Heinz is discussing, but I think it's okay because it's kind of complementary kind of stuff that we tend to emphasize. And it reminds me of a talk which I once heard from Martin Rees. And he said there are two kinds of people who are working in, he was talking about astronomy, of course. There are these chess players. And these chess players are very precise, and they make very precise statements. It's always to be believed, correct. And I would liken Karl Heinz talk to a talk of a chess player. And then there are what are called mud wrestlers. And in India, there's a state in northern India where this is very popular, where you get into the mud and wrestle, and these are dirty people in that sense, and they get into all kinds of dirty things. And most of the time, you may not need to necessarily believe that. Okay, so my discussion of mean field dynamo is in that spirit, and I'm going to talk a little bit about that today, being a mud wrestler and not a chess player. So let me recall for you some of the things that we discussed in our last talk, which is basically the MHD system of equations. We had the induction equation coming from Maxwell and Ohm's law. Then I discussed the fact that the field back reacts via the Lorentz force, and I just put down a very simple form of the momentum equation here. And then we discussed these simple consequences. One is that if you put the velocity to 0, then the magnetic field decays because of this diffusion term. On the other hand, if you go to the limit of the diffusivity or resistivity, going to 0, then the flux is frozen into the field. And we talked about the magnetic Reynolds number. And the talks and discussion which I'm going to be giving in the next few lectures is always focused on systems where the magnetic Reynolds number is much bigger than 1. So it makes my life very difficult because many of the things that I may say may not be fully correct and have still to be developed. And I do not know the final answer to many of the questions. And of course, it's very crucial to understand how dynamos work and saturate, and that's the aim of this workshop. But I thought today, to begin with, and to just give you a different flavor, I will ask a slightly different question for the first 10-15 minutes. A question about battery effect. In the sense that any dynamo requires some initial field to start off with. And this is absolutely easy if you are looking at a star or a planet, because the interstellar medium already may have had a field. But on the other hand, if you are looking at the first objects like galaxies, you may have to wonder where does this initial field come from. And this is something which you should also be alerted to, that if you take the induction equation, as Karl Heinz also emphasized, in the absence of any other term here, B equal to 0 is a completely valid solution of this equation. So if you did not have any magnetic field to begin with, you will never have any magnetic field in the end, if only the induction equation was correct. And so the first thing that one needs to, that I wanted to just mention, is that you need something called batteries to generate some seed magnetic field, even from 0 magnetic fields. And I just thought I would mention to you, some of the batteries that people have thought about.
But even thermal fluctuations will always have a B field, right?
Sorry?
Thermal fluctuations.
Yeah, which is pretty small in, yes.
Is that a problem?
No, pretty small in scale also.
Mm-hmm. Is that
because,
a problem?
Yeah, it's a problem, of course.
Yeah?
Yeah, then definitely if you are amplifying the thermal fluctuations, it will be a problem. Although there is a paper by Offer and somebody else, these Brazilian people who are trying to live on thermal fluctuations. Yes. Right. So I've just put down here some of the ideas that people have thought about of producing the first seed fields in the universe. And And of course, you could always think that there is something coming from the early universe, and I'm not going to discuss that. And it's constrained by observation, and this CMB is not cold mantle boundary. This is the cosmic microwave background. And it's interesting that practitioners of different fields use the same thing, and they start thinking exactly in that line, you see, right? So for me, when I first saw Chris Jones's talk on CMB being prominently figuring there, I kind of wondered, hey, what is this? So the cosmic microwave background, and I won't explain too much about this, and this FRM is Faraday rotation measures. Both these things constrain what fields you can get from the early universe. And I'm not going to say too much about that here. I am going to say something about astrophysical batteries, because it's very interesting, again, from a physics point of view, that you will not have any field from zero field unless you have some asymmetry between the negative and positive charges in the universe. So if your universe was completely symmetric to positive and negative charges, and if all the forces which are acting on these acted exactly the same way on positive and negative charges, you would not be able to produce differential motion between these different signs of charges, except if you already had field, of course. If you already had an electric field or a magnetic field, it will affect positive and negative charges differently. But if you had zero field to start with, you will never be able to produce a field. And all the astrophysical batteries use crucially this fact that there is an asymmetry between the properties of positive and negative charges. A simple thing which you all know is that the electron is 2,000 times lighter than the proton. And so, for example, you could have forces acting on a fluid of positive charges and negative charges which will have different effects on the fluid. A simple thing, for example, is radiation. If radiation scatters off an ionized plasma, the Thomson cross-section goes inversely with the mass of the particle, and so it does not couple as strongly to the proton fluid as to an electron fluid. So if you have a ball of ionized gas in a radiation bath, and you started trying to spin this ball, then there is a frictional force on the electron fluid, but the friction is not as strong on the proton component, and that will set up a differential drift between these two components, which will of course develop an electric field, which will try to couple them back together, and any curl to such an electric field will lead to a magnetic field. So this is an example of a battery effect, where you start from zero fields, and because of asymmetry between the properties of the charged particles, you produce some finite field. A battery which is very popular was invented by Biermann, called Biermann batteries, in the context of stars, and it can have applications even in wide range of other settings. And that the idea is quite simple, that if you have a pressure gradient in the ionized plasma, since the inertia associated with the electron fluid is smaller than that associated with the positive charges, these guys will try to run away. Once they try to run away, an electric field will develop, which will couple them back together. In the context of an atmosphere, like, let's say, a plane parallel atmosphere, this electric field has only a divergence, and it will lead to a small charge density in the plasma. But if you have context where the electric field which you develop as a curl, then the same Faraday's law of induction, which tells you that if you have a changing magnetic field, it will produce a current in a loop, will also tell you that having any curl to the electric field will produce a changing magnetic field. So this is also like something like the tail wagging the dog, an analogy, because usually in school at least, we are always taught that you take a loop of wire, you take a magnet, you put it into this loop, and you change the flux through this loop, and you drive a current through that. You are never taught the other way around, that if you start making electric fields with curls, you will start changing the magnetic field. So this battery works on the principle that you develop electric fields which are proportional to the pressure gradient in the electron fluid, and these forces balance. The pressure gradient is balanced by the electric force. The protons are more or less, can be assumed to be almost not moving at all, and that's why this comes in. And so you get an extra term if you take the curl of this, which depends upon the gradient of pressure cross gradient of the density. If pressure gradients and density gradients were parallel to each other, and this is normally the case in many contexts, then you get no curl, and so you get no field. But there are several contexts where the pressure gradients need not be parallel to the density gradient. The context which was discussed by Biermann was in rotating stars, where there are circulations which, under equilibrium conditions, these two are not parallel to each other. In the context of the universe, for example, we have discussed cases where the universe gets ionized due to sources turning on. Then the temperature gradients are perpendicular to these ionization fronts. Pressure gradients, the density gradients can also occur where structures like galaxies are going to collapse. And these need not be related to each other. There can be a source of ionizing photon like a quasar or an active galaxy or a young star-forming galaxy, which has nothing to do with the density gradients which are going to later collapse to form galaxies. And then you can produce a magnetic field just by this effect. Turns out to be pretty small, 10 to the minus 19 Gauss or so. So very far from the kind of field that is required. But it is a field coming from nothing, from zero field. And it's also coherent on the scale of the ionization front, which can be many tens of kiloparsecs or even megaparsec scale if it's a quasar ionizing front. So you automatically produce by such a battery effect coherent seed magnetic fields all over the universe. And it's like blowing smoke rings as these ionization fronts go through the to ionize the media. And then, of course, there are this formula is quite interesting because if you go to a laser generated plasma in the laboratory situation, you can actually measure. So you have a plane parallel target and you shine a laser and you vaporize the stuff and it expands out in a spherical kind of region, but there is a memory of this plane parallel gradient which was there originally. And you again have a non-parallel pressure and density gradient. And then the fields that you get are of order of 1000 Gauss or so. And this can be measured and has been measured in the laboratory. The only difference between such a battery in the laboratory and such a battery in the universe is the scales are of the order of centimeters in the laboratory, and the scales are of the order of 10 to the 20 plus centimeters in the universe. And there is an inverse scale dependence here, and that changes the 1000 Gauss to 10 to the minus 19 Gauss. The physical principle is exactly the same. And so these batteries are quite popular. As I said, there are also batteries due to gamma electron-proton scattering asymmetry. People normally do not worry too much about these first batteries because they always assume that the first stars would seed and the first active galaxies through their outflows will seed the first galaxies with magnetic fields. But this, of course, puts the problem somewhere else. And you need to know, how did the first star get its seed field? Or how did the first AGN accretion disk get its seed field? So you're just pushing the problem back. So the first time you get magnetic fields in the universe, if you do not believe in exotic processes happening in the early universe, is always due to one of these battery effects. The final thing is that they always produce fairly small fields, and you need a dynamo to amplify the field. The other aspect of this first seeding by supernova or AGN is that it's extremely difficult to mix regions which have magnetic fields with regions which do not have magnetic fields. You need to do something non-trivial to take a region which has a field and a region which does not have a field, mix it so that the plasma, everything gets the field. Okay? So it is not at all absolutely clear and not much work has been done in this.
But why can't it? Just normal, say, turbulent diffusion would do that. If both are thermal plasmas, why? Why is it difficult?
Okay, if they are both thermal plasma, you have a better hope. But when you are doing this, you will also decrease the coherence scale of the field. And secondly, even after you do normal thermal turbulent diffusion, right, turbulent mixing, you will have pockets. At the smallest scale, you will have pockets of magnetized and unmagnetized plasma. And some of the particles have to get onto the field. Okay, so finally you have to have some microscopic thing which is going to occur. It's a problem which is not yet well worked out. That's all I want to say. So bottom line, of course, is that you need dynamos to explain the observed fields, and that's why I'm going to, okay, I don't want to do this. This is just a simulation of cosmological reionization of magnetic fields produced during reionization. These are, so it's too bright here, right? I don't know why. Okay. These are magnetic field strengths color coded, and you can see that these bright green regions where the first structures are forming are like 10 to the minus 19, 10 to the minus 20 Gauss. This is temperature, this is gas density, this is a neutral hydrogen in this place, etc.
Do you see any signature of these primordial fields on the 21 centimeter wavelength?
This field is too weak to leave signatures on the 21 centimeter. But if you produce fields in the early universe, recently Shiv Shetty and I have a paper on the 21 centimeter signatures of such fields. They will affect structure formation, and then they will lead to characteristic signatures on the 21 centimeter. Yeah, you can find it on the net. But I'm putting on my dynamo hat here, of course. So I come to the mean field dynamos. And to some extent you will find that my discussion, is a kind of repeat of what Karl-Heinz has said, but I want to kind of take the bull by its horn, so to speak. The bull being a high magnetic Reynolds number system, and show you how ignorant we are at present, but some of the hopes that one has at present also. So that's why I'm saying I'm a dirty astrophysicist, because this is the problem that we have at hand. All the astrophysical systems that we have large magnetic Reynolds numbers, and we are going to be trying to do mean field theory in the presence of strong fluctuations. So, what can one do this? Let me first go through the standard thing, which you have already seen, that in the turbulent mean field dynamo, you consider a flow with a large scale velocity, u bar, and a turbulent stochastic velocity, small u. You split all quantities into an average and a fluctuation. And Karl-Heinz already nicely went through the different rules that you would like the averages to satisfy. And I think he called it R1, R2, R3, R4, probably the same things. And I had not seen his slides at all before I put this slide, but of course, this is lifted from the review from its action, and we are, of course, strongly influenced by what Karl-Heinz is writing. And the average, as he's explained, can be a volume average over some intermediate scales, or an ensemble average, or some average which satisfies these rules. And then you average the induction equation. So when you average the induction equation are a u cross b and an eta curl p. Those are, this term is easy to average, there's only one b there. But this term, u cross b, there is not only a u bar cross b bar, but there will also be u bar cross small b average, and small b average is 0, so that drops out. There's a small u cross b bar average, and small u average is 0, so that also drops out. But there's this quadratic term, small u cross small b. which does not necessarily drop out. And that's what we have been discussing in great detail, called the electromotive force. To write this electromotive force back in terms of the mean field, if at all it can be done, is a major aim of mean field theory. Here I actually like a quotation which I heard from Eric Blackman. So he said, do not ask if the mean field theory that you have is correct, but ask what should be the correct mean field theory. And this is the spirit and philosophy which I will be trying to follow. Okay. Of course, also as Karl-Heinz emphasized, finally you have a dynamo. You may want to interpret it in terms of means and fluctuations and various things. So, to find this, what this mean electromotive force is, you take the induction equation and you subtract out the mean field equation. And you write down an evolution equation for the fluctuating magnetic field, small b, which will have all the terms which has gone to 0 in this averaging. So you will have a u bar cross small u cross b bar, and a minus eta curl small b, and then there is this term, which I think Keith Moffat has called the pain in the neck term. At least that's where I heard it from. And it's basically the quadratic quantities, small u cross b minus average of small u cross b. And finding this turbulent EMF is a closure problem. Now, you may think that if you specify the velocity field, you are okay. In some sense, that's true, but actually finding this in terms of, so you have a quadratic correlation here, and you want to try to write it in terms of something which was just the average of the field itself. And this is the problem, which is a major problem. And what you saw was that in some contexts, one may be able to write the turbulent EMF as something proportional to the mean field itself, something proportional to the curl of the mean field, in a long series of expansion terms. And the important term I have not put here is dB bar by dt, which Karl-Heinz had. And we have been discussing the alpha effect of the turbulent diffusion. This is a turbulent diffusion because with such a term, if you plug it in here, it goes and sits exactly where the eta is. And so it just adds to the microscopic resistivity, a turbulent resistivity. And the aim is to calculate alpha and eta, if you want, in an isotropic kind of situation. I'm going to go through a series of plausible calculations which people have done and discuss their difficulties. The first thing which you could imagine is that suppose you are specifying u, you try to write the u cross b average as an average over u and an integral over of dB by dt. I think I should have put a t prime here, over time. This itself has various terms, as you can see here. And the important term which seems to lead to something non-trivial is this term. Because if you switch off this term, you may not get any electromotive force which depends on the mean field itself. So let's focus on that term. Okay. There's various things. Okay. If you focus on that term and expand curl of small u cross b bar, there are two terms. One is u dot grad b bar, and the other is b bar dot grad u. And I like to put it in this form because you can see that this u dot grad b bar is an advection of the mean magnetic field by the fluctuating velocity field. Whereas b bar dot grad u is a generation of more field from the variations in the fluctuating velocity field. Such kind of advection terms automatically occur in any random media and transport of something which is frozen into that media. For example, it could be, as I was explaining to one of the bunch group that we were discussing, it could be the smoke. So if you are a smoker, which most people have been banned from doing, and some people will protest, you smoke at one end of this room, and you kill the guy at the other end of the room. Okay? And if it was only microscopic diffusion which was responsible for the transport of smoke from one end of the room to the other, you can make a simple estimate at room temperatures, etc. It will take about 3 days for the smoke to be smelled there. A couple of days. So by that time you will kill an arbitrary person. You don't care. You won't kill your friend who is sitting in the audience. But on the other hand, if you take into account the fact that the air around us is turbulent, and there is a random walk of the particles over very large scales, length scales compared to the microscopic mean-free path, then the smoke will diffuse very rapidly from one end, and you can actually smell it almost within a few minutes of some guy smoking in this room. And that is what turbulent diffusion does. Enhances the transport, in this particular case, of smoke. In the case of the magnetic field, life is more complicated because it's a vector field which is frozen into the fluid, and not a scalar field like smoke. And so, not only you get one term, which is the transport of the mean field due to the random velocity, which is the turbulent diffusion of the mean field in an enhanced way compared to the microscopic diffusion, you also get another term, which is the generation of the field from the gradients in the velocity. This is what the flux freezing gives you. If you have no helicity or no handedness in the random velocity, this term leads to the presence of the fluctuation dynamo if the magnetic Reynolds number is large enough. In the presence of helical motions, it is this term which is responsible for the alpha effect, or the generation of the magnetic field, mean field from itself. So of course this is now some algebra. If you want to average this, you stick it in here, better to go to component forms and average quantities like this. And I think you should all, even whether you believe in mean field theory, not believe in mean field theory, work this out once. So how do you work such a thing out? You use this nice property that I'm usually sticking to, the simplest possible things where things are statistically isotropic and homogeneous. And if you look at all the symbols here, things which are repeated are being summed over, for example, here. And here things, same way here, you will find that only two indices are surviving. In this particular case, it's I and P, because J is being summed over, K is being summed over. So if you have a tensor quantity, which depends on two indices, I and P, then it must be proportional to delta IP, if it's isotropic homogeneous tensor, which Carl Heinz was explaining. So you write this whole thing as equal to delta IP, and then take the trace, and you'll find that this, what you have here, is multiplied by delta IP, that will give you a BI here, and the trace of this will straight away give you this U dot omega term here. If you want, I can go through this algebra, but I would recommend that you should do it. Okay? I'm just telling you a simple way to do it. And you have to do it once in your life. Similarly, this quantity here, okay, whenever there's a 3 index symbol, I always get completely confused. So I look at any 2 index symbol. Suppose you take UJL. Again, this can only depend upon delta JL into some quantity. And again, I take the trace, and I'll find that this is exactly this epsilon I jk will lead to a curl going on the other side, and this coefficient here will be just U dot U, 1/3. These 1/3s come from the fact that traces of delta ij gives you factor 3. Okay, so do it, please. By this group discussion, you should have done it. I'm not doing anything very fancy here. So, if I did this thing, then I have the following expression for the alpha and the eta, which I've already seen. And the question is what this guy is, and already you have been warned sufficiently that there are integrals here which you need not always be able to take out. But if you imagine that the velocity fields are not correlated for more than some correlation time, you would say this evaluated at the same time and then multiplied by a correlation time. In that case, this is related to the kinetic helicity, and this is related to the mean square velocity.
In the way you write it, it's indeed correlation times the average you were talking about. But can it be that this correlation time, if it different lifetime of the edge, it can be under the average?
Yeah.
You mentioned that you have different edges, then probably for differentialization, maybe
absolutely.
To
it could be. In fact, one of the things which I learned from Dmitry Sokolov was that you should probably put the average throughout here. Agreed. It could be.
Edge lifetime instead of tau correlation, right?
Yeah. And it
then it becomes a random quantity. It can be averaging over all three.
Yes, could be. But any of these is just a estimate rather than anything rigorous. That's why I'm saying I'm a much wrestler than a chess player at present. I'm going to come to, so this all looks plausible, but there is problem. Immediately, I mean, you seem to have done some kind of sleight of hand or a magic trick or whatever it is. And what you have forgotten, of course, is the fact that there are other terms, in particular the pain in the neck term. This term, okay? And you have forgotten that because you have just said, I will neglect whatever is inconvenient to me. And this philosophy which I learned from Anwar. Correct, nice philosophy actually.
Oh, come on, no, never.
But it's a good thing. Then you will of course have to face difficulty as to what to do with it. The major difficulty is that this nonlinear term which you have neglected, okay, so you can now call this approximation, and if you want to make it sound plausible, you give it a name. So, for example, in the plasma community, such a thing would be called a quasi-linear approximation. So, because you are neglecting some nonlinear term. But of course, if you are doing it in the limits in which you can do it, which Karl Hans discussed, then it is traditionally called the first order smoothing approximation. And that's because, as he emphasized right in the first step, you are assuming that the field is basically smooth. There is a mean field which is nicely dominating, and there are fluctuations which are small. And that's what gives you this picture that there is a smoothing approximation which you are making. Okay? But of course, you can also call it the quasi-linear approximation. I already discussed, and as I said, I'm trying to take the bull by its horn, that this is absolutely not the case in a high Reynolds number system because of the fact that fluctuations grow due to the fluctuation dynamo fairly fast and many times faster than the mean field can ever grow. Of course, this need not invalidate what we are doing, but we have to discuss it at least. So let me discuss one context in which you can still derive rigorously, because it's developed by the Russian school, I would think, the mean field equation, without worrying about the fluctuations. And I'll tell you why. This is if you have what I already mentioned called the delta correlated velocity field. So it's a fairly artificial velocity field, but it's good to go through a set of examples where you can do something before trying to say, before trying to discuss all the difficulties. In this, suppose, for example, the fluctuating velocity field had a very short correlation time. Okay? This is also in some way related to what Karl-Heinz said. Even if you have your Q going to infinity limit, you can have by tau correlation going to 0, but here you can do it more or less precisely here. What you do is you start with a full induction equation. You don't necessarily need to split it into mean and fluctuations to begin with. And first write down a formal solution. So at a time delta t, b at a time delta t is the b initial plus an integral or whatever was on the right hand side. Curl of u cross b minus eta curl b. And of course suppressing all the spatial dependencies here, which are all evaluated at the same space point here, of course. Now, you find an iterative solution to this. At the 0th order, completely throw all this out and put b at delta t equal to b0. Okay. At the next order, plug back b0 into these integrals. And you should actually go to the next order still, where you plug back b1, which you get back in place of b. After iterating twice like this, and you need to iterate twice because in any kind of diffusion problem, the distance you travel on the average goes as t squared, delta t squared, sorry, other way around. L squared goes as delta t. Okay? So if you want to keep things correct to order delta t, you need to iterate twice. So when you do this iteration twice, and then you take the average, then you get firstly the average of this, then you get average of all the smooth quantities times delta t, which can come out of the integral, because I'm only doing for a short time here. And then you get this messy looking thing here, which is iterated twice. So the first time you had a curl of v, fluctuating velocity cross b. By the way, now I have switched to v instead of u. And this is due to Axel's influence. Because any good velocity field, he said to me, must be u. And if it's delta correlated, it's a bad velocity field. So let's call it v. So I've switched to v here. Okay. And so this was coming from the first iteration, and then when it got plugged back here, this another v cross this whole thing comes from the second iteration. So far I have done nothing very dramatic, but the interesting step is now is to notice that if velocity field is delta correlated in time, in this ideal limit, then from one instant to the next instant, the velocity does not remember what it did before. So it's a completely random at every. So it does not care what the magnetic field did before. So this averaging over all this guy, and this is in fact incorporating that nonlinear term. We have not done any split of mean and fluctuations here. The crucial step is that v at time t in this integral is not correlated with b at x at time 0. So you can split this average into an average over just the velocity and an average over the magnetic field. So, because of this, you get back, this quantity is nothing but what we had in the previous slide. This quantity v cross curl v will be nothing but what we had in the previous slide. You will get all those alpha and turbulent diffusion multiplied by delta t into b bar. So you get back this mean field equation. And you have not done this split of mean and fluctuation and throwing out the nonlinear term, nothing. But what you have done is to use this fact that the velocity field at any time in this flow, in this artificial flow, does not care about what the magnetic field did at the previous time. This is what allowed you to split this averaging. and go to the mean field equation. So this is not my, this you can find in a book by Zeldovich, Uzbaikin, and Sokolov, this kind of discussion. And it was probably, and was and no, developed by, I guess it's Zeldovich, right?
Zeldovich, Molchanov, Sokolov, Uzbaikin, they all.
Yeah, so this all goes back to that work, of course. It's not new.
No.
This is the only clean context where for a large Reynolds number system, you can get the mean field equation of the form that you're familiar with. What happened to all the fluctuations? Because as I said, the mean field, in the presence of fluctuations, you will always worry about what is mean, what is fluctuations. In this problem, in this flow, we already discussed it, that this is the Kazantsev flow where there is a fluctuation dynamo. The mean field does its own thing, the fluctuations do their own thing. Both of them are growing, they both satisfy. So, it's like this, you have a stochastic partial differential equation. Because this velocity field is a stochastic quantity, random quantity. In this particular case, it's delta correlated in time. Then you ask, what do the moments of this equation do? Moments. The first moment is the mean field. And that obeys this equation, as I derived in whatever rough way. The next moment is the correlations of the field, the 2-point correlations of the field. That will obey some modified version if there is a mean velocity of the Kazantsev equation. So let me just discuss that. So the fluctuations are doing their own thing. And we already discussed that, okay, here at least I have written out properly, that this is exactly the Kazantsev problem where you have velocity correlations which were delta correlated in time, but there are some correlation functions in space. So far I have not put any helical piece to this correlation function. And this delta correlation in time helps you to write differential equation for the magnetic correlations. So here, just to familiarize you with the notation, delta ij is something which you expected for isotropic homogeneous tensors. But if you have 2 points separated in space, there is also a separation vector. Then you ask, what are all the isotropic homogeneous, what are all the things which, because of homogeneity, this correlation can only depend upon x minus y, which is the separation vector. And because of isotropy, this correlation tensor can only depend upon quantities like Ri, Rj, or epsilon ijk and r. I have not yet put that term in, it will come in the next slide. But if that term is there, you will have helical parts to your velocity field. But without that, you have a purely non-helical random velocity field. In fact, the turbulent diffusion is basically this correlation function, TL, or the longitudinal piece evaluated at the origin. And you can look for solutions to the induction equation where the magnetic correlations for the fluctuations are also split in this form. Of course, here I have right now put the mean velocity field to be 0 because the alpha effect and the turbulent diffusion do not worry, you are not really worried about the mean velocity field. These magnetic correlations turn out to satisfy an equation derived first by Kazantsev. This is an equation. There are two terms here. One is some kind of an effective diffusion term, a scale-dependent diffusion, and one is a generation term. This generation is nothing but gradients of the velocity, and you will be like whatever I said, velocity shear. This diffusion at the origin of the correlation function is just microscopic diffusion. Far away it is just turbulent diffusion because this goes to 0. And a very interesting thing which was pointed out by Kazantsev was that you can transform this problem into a quantum mechanics type problem by making the following substitution. I put psi here just to make you think about quantum mechanics. And if you make this substitution here in this equation, you get an equation which looks just like the steady state Schrodinger equation. Now minus gamma, so I have said that I want to look for growing solutions of exponential 2 gamma t. But minus gamma acts like an energy eigenvalue. The turbulent diffusion inverse of that acts like a mass. And there's a potential which I have not written down, which is a bit complicated. So it's like a bound state problem, because if I want gamma to be positive, I want the energy to be negative. So you look for bound states basically in this potential. And the growing modes of the dynamo correspond to bound states in this potential. Well, there was a spatially dependent mass term, of course. And there's a lot of interesting work since then on this problem. And you find that you will get growth rates of the order of the stretching rate, and field is concentrated on these scales, things which we qualitatively mentioned. So why am I mentioning this? Is that for this velocity field, delta correlated velocity field, we derived a mean field equation. We did not say anything about the fluctuations. For the same delta correlated velocity field, we derive a fluctuation equation. And both do their own thing. The mean field obeys the mean field equation, the fluctuations obey the Kazantsev equation. Okay, at this linear state, at this stage where there are no Lorentz forces, both can lead to growing modes. There will be eigensolutions of this which lead to growing fluctuating fields. At the same time, there will be solutions to the mean field equation which is leading to growing mean fields. The difference which has happened is that even when the Rn is large, it's not only the means which are growing, but the fluctuations are also growing. And both are doing it independently, without any problem. Of course, I have not put here helicity, and in fact it's very interesting what happens when you put helicity, and I really have the temptation to show this, because when I first discovered this in a different context, I was very pleased to think about it this way, because I always admired this picture about bound states. So if you put helical pieces to the correlation, and there's a long history of this, these are all different people, Weinstein, Kichagina, who first derived these equations, and Lokchelsky and Klurin, and then I had a paper in 99, then this must be Kim and Hughes, David Hughes, who also derived these equations. Then you get for the magnetic correlations both a longitudinal and transverse correlation function and a helical piece also. In fact, physically the helical piece is something like the current helicity correlation, and these are something like BV correlations. And instead of one Kazantsev equation, you get two coupled Kazantsev equations, both for this ML and for the C. Okay. And for, oh, I put C in both places, no, I put C here. Should have been H here, sorry. I've just changed the notation. Oh yeah, it is okay. It's C, and C is related to H in this way. Now it turns out that these equations have very interesting behavior. You could imagine that you have an infinite system, and you have just random stirring with the Kazantsev delta correlated. In fact, turbulence people also put Kreitmann's name there, because he also discussed the same velocity field in the context of passive scalar evolution. So many people call it Kreitmann Kazantsev or Kazantsev Kreitmann, depending on your preference, of course. Velocity field. So if you had this random stirring going on, and you looked at the dynamics, there is nothing in your head to prevent you from considering all scales, scales which correspond to the scale of the stirring, and scales which correspond to scales bigger than the stirring. So there is no need to actually split mean and fluctuating field at present. If you have an infinite system, you will get all scales being generated. And in the presence of helicity, something remarkable happens. As you go to very large scales, as you go to very large R, brings large separations. All these terms die out. But it turns out that this term, the helical terms in m dot and h dot, remain. And they themselves lead to correlations growing on very large scale separation. That means you have a larger scale modes excited than the scale of the stereo. I discovered that there was an interesting way of looking at this. Suppose I look at the same system when there is a quasi at a critical state, when dml by dt is 0 and dh by dt is 0. As I will discuss in the future lectures, helicity can never stop evolving. And the microscopic diffusion will always lead to a slow evolution of the helicity. But if I consider quasi-static kind of states, evolving states, then in that case, you can write a similar Kazantsev type equation. You can combine those two equations to write a similar, you can eliminate and write one equation. The only thing which happens is that the potential which Kazantsev considered, instead of allowing only bound states, usually it would have gone off to infinity like this. Okay, this alpha term is not there. Or sorry, it would have gone like this and been positive definite always. It will allow only bound states up here. Allows in this case, because of the alpha effect, this potential goes to negative values, and I am looking at zero eigenvalue states, so it allows for you to have a tunneling state out. So in this kind of a picture, which I don't expect you to appreciate straight away unless you go through all the maths, the fluctuation dynamo corresponds to bound states in the corresponding quantum mechanical problem. But once you have any kinetic helicity in the system, it allows for these bound states to have, instead of just having bound states, it allows you to have free particle states suddenly. In that sense, it changes qualitatively the nature of the system from something where correlations are just confined to regions where you initially stirred the system. If you stirred it on some scale, all your magnetic field will only be on those scales and below. The presence of helicity allows you suddenly to have propagating states, allows you to have correlations on a scale bigger than the scale in which you stirred. And that's an interesting aside. So really speaking, once you have helicity, it turns out you have three scales in the problem. You have firstly the stirring scale, in which you make the fluctuation dynamo operate. You have this random, this scale determined by the alpha effect, which turns out to be, if it's a fully helical system, just 2 times. The maximum growth occurs at 2 times the stirring scale. Then this whole thing, you're putting it in a big system like the galaxy or sun. You have the scale of the system. Okay? And I think maybe Alex sometimes calls this a mesoscale. So you have these 3 scales in the problem.
Andrew, the fastest growing modes are always on the stirring scale.
Yes.
That's
Right.
Small scale dynamo will always
Yes.
grow faster than
Absolutely.
the large scale.
Right. But except that they are not influencing at present at the kinematic stage
Yeah.
anything to do with the mean field dynamo. That's the only point which I wanted to make. Yes. The fastest growing, as Chris has said, are always on this scale. But these are not that much slower if it's fully helical. It is just factor of 2 slower, the intermediate scale. The system scale will be much slower because that is a big scale there. Now, so the thing which I wanted to convey in that example is that here is an example of a large Reynolds number system where you have fluctuation dynamo, but the mean field dynamo equation is not wrong at all. Okay? Even though you cannot use first order smoothing or quasi-linear approximation to derive this equation. Now I want to present one more example of this, which I found to my surprise buried in the literature, and maybe the authors of this paper did not I have to alert them saying that it's a very interesting piece of work. This is a paper by Andrew Gilbert and Bailey in 1992 in JFM. And when I discovered this paper, I was really amazed. It's very cute and very nice paper. And we have been doing something on this. So this idea is not new, and in fact, again, it has been considered by many people in the Russian school. Dmitry Sokolov has many papers on what are called renovating flows. And Advar tells me Parker did something right in the beginning, right?
No, Parker separated.
Oh, okay. That I'll come to later.
Stretch shearing and diffusion.
Yes. So a renovating flow, see, the delta correlated flow you may think is absolutely artificial. Slightly less artificial is a renovating flow. Because here what you imagine is that you imagine that you have a flow for a certain time tau, let's say. After this time, you completely change the flow randomly. And keep doing this at every intervals of time, tau, 2 tau, 3 tau, etc. So such a flow is what I call a renovating flow. It liberates you from the delta correlation. Because delta correlation is really zero correlation time. So here you can have a finite correlation time when the flow is all correlated. There is nothing which is, you have a given flow. The flow which was considered by Gilbert and Bailey in this paper was a simple thing like this. Basically, they took a velocity field, which is a sine and a cosine, and a coefficient h, which can be ranging from +1 to -1. And the presence of this h makes this flow helical. If the h was not there, the flow will not be helical. So these are just plane waves, basically. And divergence of u is 0 imposes the condition that A dot q is 0 and B dot q is 0. So you choose, if you want to describe orthogonal system, B to be orthogonal to both q and A. And this whole system is specified. Now you ask what happens to the magnetic field in this renovating flow. So in general, what you imagine is that, for example, the phase of the flow changes randomly between 0 and 2 pi. In each time interval, I choose an arbitrary phase between 0 and 2 pi. In each time interval, I choose an arbitrary direction for this q vector. In this particular example, they kept the magnitude of q the same. And at each interval of time, I can even choose arbitrarily what is the amplitude vector. So in principle, it's fairly general, although I'm going to keep the amplitude the same. I will only allow psi and q to be random. So in any time interval, you can choose this randomly, and in any time interval n tau, at a time n tau, you can relate what happens to the magnetic field at a time n minus 1 tau by some general kernel or a Green's function or whatever Karl Heinz called it. So the B at time n tau is related to the B at a time n minus 1 tau by integrating over some Green's function, Gij(xy). If you can calculate that Green's function, it's a fairly interesting problem to have solved. And Gilbert and Bailey calculated this Green's function in an interesting limit. They said, this flow, let's divide it each time interval into 2 halves. One half of the flow, you forget diffusion. You let it only be flux freezing evolution. In the other half of the flow, you forget the velocity and you let it be just diffusion. For each half of the flow, you can write down the exact Green's function. If you can integrate the trajectories of this, you can write down the exact Green's function. So for each time interval from n minus 1 tau to n tau, you can write down exactly what is this Gij. Now, if you have arbitrary phases for here, okay, this whole system is basically a homogeneous, statistically homogeneous system. So if I want to consider the evolution of the mean field in this system, if I take average here, this average here will depend only upon x minus y to begin with, and more importantly, because it's a renovating flow, the Green's function which you have here will not depend upon what the field did at n minus 1 tau. That's just some initial field. It will not be correlated. The velocity field is not correlated with what the field was at n minus 1 tau. In the time interval between n minus 1 tau to n tau, you have just some arbitrary, randomly chosen field, which had nothing to do with what the magnetic field looked like at n minus 1 tau. So again, the clever thing here is the decorrelation between the velocity and the magnetic field at some earlier time. So if I take average here, it's just average of this Green's function times average of this field at this time. Average of this Green's function, since it only depends on a statistically homogeneous system, only depends on x minus y here. And so it's much more convenient to go to Fourier space, because there's a convolution in physical space. It's a multiplication in Fourier space. So you go to Fourier, take different Fourier components. So there are different Fourier components of the Green's function multiplied by the different the Fourier component of the magnetic field. Only complication is this is a tensor, that's a vector type. So to sum over those indices. So the whole idea is to calculate this Gij, average K. Once you calculate this, how do you know whether the mean field grows or not? Yes?
Sorry, in terms of the correlation, the B in some blob of flow in time n is going to be the initial conditions for time n plus 1. So during that correlation period,
The B.
The B is going to evolve according to this initial condition.
Yes. But the velocity field statistically has no correlation at any time with the magnetic field which started as the initial condition. So
the velocity is changing arbitrarily, but the field is going to...
Yeah, now in fact I'm going to evolve that field. The Gij has to be calculated by how the field evolves. Right. So you have an initial field, but I can decide to push it this way, some other way, right? And so this is, so if I take an average, some property of the velocity field, product with the magnetic field, I can split this averaging. That's all I'm saying. Now, suppose you have this Gij calculated, you look for eigenvectors of this. If you have an eigenvalue which has a modulus greater than 1, then if I keep applying this operator again and again, okay, so from initial condition to tau, then to 2 tau, then to 3 tau, I will get modulus of that eigenvalue to the power n. So if I multiply these numbers repeatedly, if I take a number which is smaller than 1, then I will get decay. But if I take a number which is larger than 1, I will get growth. So the condition for growth of the mean field is that the eigenvalue sigma has to have a modulus greater than 1. And then you can find the growth rate, which is just you plug in e to the lambda t is equal to this, and the growth rate will be this 1 upon tau into log of sigma. So this is what we will do. Before doing this, I just thought I should mention one more thing, which is, for the students, of course, flux freezing revisited. This many of you may know already, of course. We were always thinking about flux freezing as something where the flux through a loop is frozen, but there's an equivalent formulation of flux freezing which is very interesting. I think you can find it in Landau-Lifshitz. That's where I found it, but probably known to many people even before, which is called the Cauchy solution, where, because, the reason I'm going to use this, or I'm not going to tell you the detail, but the reason I'm mentioning this is that I'm splitting each subinterval into 2 intervals, a flux frozen and a pure diffusion. During this interval, it will turn out that I can write the B at one time to the B at the earlier time by just a coordinate transformation of the final coordinate with the initial coordinate. And during diffusion, it's purely a diffusion Green's function, which everybody is familiar with. So how does that come about? And it is just recasting the induction equation. It's just something which is standard textbook material. And if you look at the induction equation, you can rewrite it as dB by dt plus u dot grad b is b dot grad u minus b divergence u. We wrote this down right in the beginning. But if you look at it this way, you can eliminate divergence u by using the continuity equation and write down the following equation for b by rho. The Lagrangian derivative of b by rho is b by rho dot grad u. Now if you take two particles in the flow, they are flowing at different velocities, u at point x and u at x plus delta x at point x plus delta x. And if you look at the equation satisfied by the separation vector, okay, it will be the velocity of the separation vector is exactly the same equation. I don't know whether I'm making myself clear. If you take 2 points, this is going at u x, this is going at u x plus delta x, but this is the separation vector, let's say delta x. Then this dy dt, what I have written of delta x, is just the change in velocity of these two particles. So it is u at x plus delta x minus u at x, which to linear order is just delta x dot grad of u. Okay? So that's this equation. Now you see that these two equations are kind of identical. So for example, if you just subtract these two guys, okay, if initially you find, if for example initially at time t equal to t naught, fluid particles are on a given magnetic line. So suppose this was a magnetic field line, and you take 2 points on the field line. Okay? Because they satisfy the same equation, if b by rho initially at some t naught and x naught was on this line, so there is some constant multiplied by the separation vector. Separation vector gives the direction, the constant gives the magnitude. If I subtract these two equations, okay, you will get the subtracted quantity to, if I plug this in, they evolve in the same way, this relation will always be maintained. So b by rho will at all times be c naught into delta x. So this is like saying that b by rho is proportional to n. So you can use this to write b at a time t to b at time t naught by just the Jacobian of the transformation between x and x naught. This is the initial position, this is the final position. So given this velocity field, if I can integrate the trajectories corresponding to this velocity field and just take the Jacobian of the transformation, I will know exactly how the field behaves from n minus 1 tau to n tau during the flux closure evolution. And I will know exactly how the field behaves during the second thing because it's just pure diffusion. Then it's a question of averaging over all size, over all q's and all that. And this I gave as a student project to Sandeep Kolekar, who appeared in the slide, in the first slide of mine, who is now doing quantum gravity. So, but he did a project with me on dynamos. And now I'm calling him the master of averaging. Because Gilbert and Bailey have got maybe the Russian influence of not giving any intermediate steps. Okay, Andrew Gilbert, I know, is very, he generally doesn't project himself very much in this thing. So they just give the final steps. So Sunway did all the averaging. And what you get, and I'm going to quote the result only for the fully helical case, where h is plus 1 or minus 1. And this matches with what Gilbert and Bailey get also. This Green's function in K space is a delta ij into J0. Remarkably cute result. J0 is a spherical Bessel function, sine x by x. Multiplied by an epsilon ijk term into J1, and the tau comes here. You can see that correlation time is coming here. Okay, here and here. And you can easily find the eigenvectors. And what are the eigenvectors? It's something which you would guess are the eigenvectors. It's just fully helical waves. The eigen solutions to this, eigenvectors, are basically plus minus I, 1, 0 is one eigenvector. K itself is an eigenvector because it's killed by this term, and delta ij makes it k, but k is not allowed because the magnetic field has to be transverse. So that eigenvector is not allowed. The two eigenvectors which are allowed are the two helical waves which you can have. And the eigenvalue is just all these Bessel functions. These are the eigenvalues for those two eigenvectors. And so you can find the growth rate, which is written out explicitly here. T is because you have a scale for the velocity field Q, and you have an amplitude for the velocity field A, you will have a turnover time scale defined naturally, and that is this T. And there's a log of all these Bessel functions. Remarkably, this is something which they just mentioned in passing. If you take tau going to tau by t very small, the short correlation time limit, from all this you get exactly the eigenvalue to be alpha k minus eta t k squared, where alpha is the helicity associated with the flow and eta is the term v squared associated with the flow, the original flow which I defined. This one. This velocity field, you can take an average of u dot curl u over all space, and you can take u squared average. And the alpha and eta are exactly related to those quantities which you have there. Of course, this you can use for any time tau. You need not stick to short correlation times. And they gave also plots for this, and I got some way to plot this up. You can probably not see it very well, but this is a correlation time of half the turnover time for this. So it's almost the dispersion relation. If it was alpha k squared minus eta k, alpha k minus eta k squared, there should be this parabola. And it's almost the same parabola, except it's just missing it here somewhere. If you can now go to larger and larger correlation times, this renovating time can be arbitrary because you have solved the problem without making any approximation about how big the renovating time should be, or at least they solve the problem. Okay? And so you get non-trivial behavior, and this is the modifications you are getting because of having finite correlation time. For example, if you have very large times, you get various windows of opportunities for growth. You cannot see it. I should make him draw this figure with thicker lines, but there are these oscillations here. I mean, this is the growth rate and this is the wave number. And this is the wave number as fraction of the forcing wave number. So you can see here the maximum is at about half for this plot. That is, you excite modes of the mean field twice this length of the forcing. And this is what you expect always from the alpha square dynamo. Okay? But you will also have different behavior, and of course this growth rate in units is in dimensionless units of the turnover time. So it's like few percent, of course, of the turnover time rate, whereas the fluctuation dynamo will grow on the scale, on the rate of the turnover time itself, maybe 70% of the rate associated with the eddy turnover time, whereas this is only a few percent, so it's growing slowly. So now, but in fact, also interesting is the fact that usually we are thinking of helical dynamos and you have one sense of the forcing, helicity. You get the opposite sense for the mean field. Okay? This breaks down when you have larger correlation times. And in fact, in the other plot, which you cannot see very well, this is for, there are two eigen solutions. One has got one sense of the helicity, other has got the opposite sense of the helicity. And those can also be excited if the correlation time is large enough. When it's like 8 or 10, they pointed out that even these guys can be excited. What it means for helicity conservation, I'm not sure. But this is true. So, once again, what I wanted to say is that, yes, here is an example of a high magnetic Reynolds number system, admittedly solved in this simple way where we split the intervals of time into one where you can do flux freezing, one where you can do diffusion. Okay? But it gives you predictions for that the mean field grows. What about the fluctuating fields? It's much more complicated to do a Kazantsev equation for this system. But what you can do is a single point PDF. And what they also show in the same paper, and that's why I liken it to a Russian paper, because they do a huge number of things, each of which will take you some couple of weeks or whatever to sort out properly. They show that the fluctuations are also growing. And in fact, in the same sense as the Kazantsev dynamo, the fluctuations are growing faster for larger moments, so that the field becomes highly intermittent. But does not prevent the mean field from growing. So another example, which is now slightly removed from the delta correlator, where you have the mean field doing its own thing, the fluctuations doing its own thing. Okay? Without making all the approximation of first order smoothing or anything. Yeah, this already Karl-Heinz showed you in the morning, that when we go to the other way you can ask these questions is to test it in simulation, and this is from Sharanya Sur working with Axel, or Axel making Sharanya do various things. Sharanya, when he wrote his PhD thesis, I haven't shown you this thesis, okay, as a remark that the day he landed up in Nordita, within about half an hour or something, he was running simulations with Axel. So this, of course, I have always resisted. Only once in my life, Axel, when he visited me, downloaded the whole pencil code into my laptop. And I said, thank you very much, and I didn't look at it. Right. So this is the test field method that Karl-Heinz talked about, and he showed already these two plots. The only thing which I would like to remark here is that by the end of these simulations, where you are trying to measure the alpha and turbulent diffusion by using these test fields in a box, the fluctuations are growing like anything. And this has been always, this is also the problem because of the small scale dynamo. Okay. And you can look at this problem in an interesting way, which I just will close with, more or less. The sensitivity to fluctuations. Karl-Heinz already emphasized for you the equation for small b you can solve by treating that there is some Green's function which you don't have to worry about, which you cannot calculate, but there is some way in which evolution has to be in this way, that the small scale field will depend upon, there is an inhomogeneous forcing due to the mean field, and there is a homogeneous term. Okay. Now, if the mean field did not exist, then you took u cross b here, you should get 0 here. That's our hope for the isotropic case, because there is, even if there is a small scale dynamo, you don't know where the EMF will point. But if the mean field does not exist, still there is a fluctuation dynamo. So this part of the equation says that even if b bar is 0, only the second term survives, and this equation then has to describe a growing fluctuation dynamo. And so all the exponential growing fluctuations are in the Green's function, because this small b is evaluated at the initial time ti. So in this kind of description, when you write down for a large Reynolds number system, the Green's function is reflecting all the growing fluctuations. And the same Green's function is sitting here. And it's growing these fluctuations correlated with b bar. So even though the average stays steady. The fluctuations above that average are growing whenever you're trying to measure these things using the test field method. But does that mean that things are all wrong with mean field dynamo theory? And I don't think so, because what I've said so far is that really both, it is quite plausible, and I've just given you two fairly idealized examples, that even in a large magnetic Reynolds number system, the mean field can do its own thing and the fluctuations can do their own thing. They can both grow. If you look at a simulation, you will find that it's all noisy and there is nothing, no sign of a mean field. But that's because they're just growing faster. And what you have to figure out is what happens when things saturate. When the fluctuations saturate, what happens to the further mean field growth? Or does it happen that way, or everything saturates together? And here I think only simulations have been able to shed some light that the way to make a healthy mean field dynamo growth is to have helicity fluxes of some kind. And these will be the things which I will try to take up from my next lecture onwards. Okay, stop.
Thank you. And questions, please. You said something about that you don't know what happens to the magnetic helicity in the kinematic flow. And I think we know from ABC flow dynamos that what happens in the limit of Rm is, as Rm goes higher and higher, the net magnetic helicity is going to zero. But as Rm is still finite, the helicity is also still finite and is growing exponentially. But in the limit of large RMs, that growing part is going to zero. So there's in such a way that you have equal contributions from plus and minus, which cancel each other, of course.
Okay. Well, there are two things which I forgot to mention. One is, in the Green's function, the eta disappeared somehow. Eta is hanging around there as just an exponential minus eta k squared multiplying everything. And that was the, in fact, the other thing is, no, this remark of mine was the fact that in the alpha squared dynamo, you expect one of the, if you force it one helical wave, the mean field should have the opposite helicity.
Yeah, right.
Whereas in this, for large correlation terms, you can excite both sides of helicity. So which seems
But they cancel,
strange.
right? They still should approximately cancel for large
Yes,
RMs.
it may be that it's cancelling on the total, because it will be that it's being carried by something else, or it is being actually generated. But I don't, because there's only the mean field evolution which is being described here.
Any other questions? Yes, please. Chris.
You talked about the Kazantsev model and the delta correlated, yeah? So how small does the time correlation have to be for this picture to be valid? I mean, obviously no real flow is delta correlated, but some flows might have a short correlation time. So the natural question is, how short is that correlation time got to be?
Right. So I can't answer that for the Kazantsev thing itself, but you can see from the Gilbert-Bailey paper that this curve which they have here, right, this bottommost parabola that they have here, this one, okay, this is for tau by t of half. Okay, if it was delta correlated almost, then the parabola should be exactly like this, ending at 1 here, having a maximum at half. That would be the dispersion relation. So the dispersion relation has changed a bit, but we have not plotted 1, but it's not very. On the other hand, when you see go to 2, for example, this is now the dispersion relation. So it has changed quite a bit when the correlation time is twice the turnover time. But here we are able to address this issue concretely, that in that paper, or at least for the mean field,
Yeah.
not for the fluctuation, because that equation has not been worked out.
No.
Okay, if there are no further questions, then let's have lunch again, and then we reconvene for Anwar's talk at 2 o'clock, and then we have 3 student presentations at 4 o'clock. So that's the time for